Welcome back to multivariate calculus. In this video, we're going to be looking at polar coordinates and polar curves. We've been talking for the last little bit about the rectangular coordinate system, and I mentioned that that was actually just one of several coordinate systems that exist. Polar coordinates is the other really common coordinate system used in thinking about the coordinate plane. In polar coordinates, instead of thinking about a vertical axis and a horizontal axis, we tended to think just about a little bit of that axis, specifically the bit that goes off this way. Let's try drawing that in a thicker marker so it's a little bit easier to see. All right, we're going to focus on the positive x-axis. And then instead of thinking about things otherwise, I'm going to think about everything in terms of concentric circles. So in polar coordinates, a point is given as the ordered pair r comma theta. So if I have a random point, like let's say this point right here, I'm going to draw the line from the origin to that point. I'm going to measure the length of that line and call it r, and I'm going to measure the angle in standard position and call it theta. And so with an r and a theta, we can plot a point. All right, let me go ahead and get my head out of the way, and let's start looking at a couple of specific points. So for example, if I want to plot the point 3 and pi over 6, right? Pi over 6, remember, is something like 30 degrees. But I know that the right angle is pi over 2. So if I take that right angle and I divide it into 3 equal regions, then I've got pi over 6, 2 pi over 6, which is pi over 3, and 3 pi over 6, which is pi over 2. And 3 pi over 6 is going to be the point on the third of the concentric circles, right like that. All right, if I want 2 and 5 pi over 4, well, I remember that 4 pi over 4, or pi, is right here. 6 pi over 4, or 3 pi over 2, is straight down like that. So halfway between is going to be the angle 5 pi over 4. And then 2 rings out on those concentric circles is a distance of 2. So there's point A and there's point B. Now, if we're using r and theta to describe a point in the coordinate plane, and we've already established that we can reference any point in the coordinate plane as an x and y pair, then we should be able to work backwards and get right back to that, shouldn't we? For the sake of making SIGN sign easier, I'm going to look specifically in the first quadrant, but this should extend to all 4 quadrants. Let's take a point here, which I claim I can define in polar coordinates as r theta, and I claim I can define in rectangular coordinates as x, y. I'm going to go ahead and draw the line from that point straight to the origin. The definition of polar coordinates says that that has to have a length of r, and this angle here has to be the angle theta. I'm also going to go ahead and put in some dotted lines parallel to the x-axis and parallel to the y-axis. The definition of rectangular coordinates says that this length has to be x, and that length has to be y. And now, one nice property of a rectangle is if the length on the left is y, the length on the right is also y. And so, if I just cut out the part of interest from this figure, I get a really nice right triangle. And you probably have seen this before. I hope that you've seen this before. But given this right triangle, we can use triangle trigonometry to say that x is r times the cosine of theta. Right? Cosine is adjacent over hypotenuse, so x over r, and just multiply both sides by x. Likewise, sine is opposite over hypotenuse, y over r, and multiply both sides by y. We've also got the Pythagorean Theorem. R squared is x squared plus y squared. And I guess one last trig function we haven't talked about, the tangent of theta is y over x. And we usually think about these in two separate groupings. The first pair of equations will let us take any point given in polar coordinates and rewrite it in rectangular coordinates very easily. The second pair of equations will let us take something that's in rectangular coordinates and rewrite it in polar coordinates, although it's a little bit more of a challenge to do so. So for example, if I have, say, one of the points that I just plotted, 3 pi over 6, and say 2, 5 pi over 4. Well, just looking at the formulas we have right here, x is r times the cosine of theta. That's r, that's theta. That's really all it is. So we're going to have r times the cosine of theta. We're going to have r times the sine of theta. And we know that the cosine of pi over 6 is 1/2. I'm sorry, that's backwards. The sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. Get my head screwed on straight. So we've got 3 times root 3 over 2, and then we've got 3 times 1/2. So I guess that's just 3 root 3 over 2, 3/2 is the point 3 pi over 6 in rectangular coordinates. Likewise, for the second point, we're going to have 2 times the cosine of 5 pi over 4, and we're going to have 2 times the sine of 5 pi over 4. Cosine of 5 pi over 4 is negative root 2 over 2. Sine of 5 pi over 4 is also negative root 2 over 2. And so we get that that point is negative root 2, negative root 2. Going the other direction is a little bit more challenging. Again, just because the points and angles don't always behave as well as we would like them to. But let's say we want to take the point 2, negative 2 root 3 and rewrite it in polar coordinates. Well, we can use the Pythagorean theorem. R is going to be the square root of 2 squared plus negative 2 root 3 squared. 2 squared is 4. 2 root 3 squared is 12. So I get that the radius in this case is going to be 4. And then to get the angle, the tangent of the angle in question is going to be the y-coordinate divided by the x-coordinate. And I'm actually getting a little bit ahead of myself. I'm going to put that back as an alpha, but one thing that really gets annoying about the inverse trigonometric functions is that tangent especially is periodic with a period of pi. So there are 2 places on the coordinate plane that will give you the angle that you want, whether this ratio is positive or negative. The easiest way of dealing with that is to, instead of looking for tangent of theta right away, we're going to look for a reference angle we call alpha, and we'll just take the absolute value of that stuff on the right-hand side, and we'll figure out SIGN, positive or negative, in just a little bit. So the tangent of our alpha is the square root of 3, which means that alpha itself is the arctangent of the square root of 3. Which is pi over 3. Now we just have to figure out our coordinates. So the point 2, negative 2 root 3 is somewhere around here. And the reference angle alpha is always the shortest path to the positive or negative x-axis. So in this case, it's this guy right here. But to write a point in polar coordinates, we need to read the angle in standard position. So starting at the x-axis and moving around this way. So we try to go the whole way, which would be 2 pi complete circle. We don't quite get there. We come up pi over 3 short. Finding a common denominator, 2 pi is the same thing as 6 pi over 3. So I get that the angle in question here is 5 pi over 3. So in polar coordinates, this particular point is 4, 5 pi over 3. More interesting than just polar coordinates, what we're going to be looking at here are some polar curves. And it's possible to write any equation involving r and theta and call it a polar curve, but we'll stick to the simplest case of functions. R is some function of theta. And there are a ton of different polar curves. There are two specific polar curves that I, well, yeah, two specific polar curves that I want you to be familiar with. The curve r equals k is a circle with radius of k, and the curve theta equals h is, I'm going to call it a half line from the origin. It's a ray, but it's not really directional, so rays can get a little bit weird. But choose your direction and just go off in that direction. Those two polar curves you should be able to recognize without too much thought. More complicated polar curves, I'm exclusively going to look at through computer software. So let's jump back over to GeoGebra, and actually I guess I have to zoom out a little bit further here. There we go. Now you can see the thing that I care about, which is this keyboard icon at the bottom of the screen. If I go ahead and click on that, it brings up this window. And depending on where you are, it can take a little bit of finding to get to what we need. But specifically, I want to go into the alphabet menu, ABC, and then notice at the bottom here is Greek letters alpha, beta, gamma, and you can go in there to get your Greek characters. That is, in fact, the only way to get theta to show up in your graph, but you can go ahead and click on that, and then you have theta here, and you can type around that. So apparently theta equals 1 does not work. Good to know. But if you want something like r equals 3 sine theta, you can go ahead and graph that. If you want r equals 3 times the sine of 3 theta, you can go ahead and graph that. I do want to point out that if you want to try to graph a circle in polar coordinates, just typing r equals 3 will confuse GeoGebra. So you have to make sure you put a theta in there somewhere. R equals 3 plus 0 times theta is the same thing as r equals 3. And then the software will graph that no problem. All right. One last polar graph, r equals 3 plus 3 times the cosine of theta. This is called a cardioid graph. Again, whether or not you can recognize polar curves by their equation is not really important to me. What's important to me is that you can get into some computer software and you can graph those curves so that we can work with them from there. Another thing that's going to be important to me is that you can take polar curves or even rectangular curves and turn them into the other thing. So let's jump back to my notepad and let's take a look at this particular equation. We had r equals 3 plus 3 times the cosine of theta. A little too far there. Right. And what do I know about polar coordinates? Right. I've got an r here. I know that r squared is x squared plus y squared. I've got a cosine theta here, and I know that r times cosine theta is x. So it seems to me that the easiest thing to do is going to be actually introduce more r. I'm going to multiply both sides of this equation by r, because then I can replace the r squared on the left-hand side with x squared plus y squared. I can replace r by itself with the square root of x squared plus y squared. And I can replace r cosine theta with x. And so I can take an equation that's given to me in polar coordinates and I can turn it into something that's written in rectangular coordinates. There is not one unique way of doing this. For most polar curves, there are several different representations, and sometimes it's hard to find the most useful of the representations, but it is something that you should be able to do. Likewise, if I have something that's given to me in rectangular coordinates, for example, x squared plus 2y squared equals 6, I should be able to take this and rewrite it in polar coordinates. And once again, it's more of an art than a science. So I'm not going to claim that this is the best way or certainly not the only way of doing it. But what jumps out to me is I've got some x squareds and y squareds going on here. So my inclination is to rewrite that left-hand side as x squared plus y squared, right? 2y squared is just the same thing as y squared plus y squared. But then by putting my grouping symbols in, I've got an obvious x squared plus y squared, which is easy to deal with. I've got a leftover y squared, but of course I know that y is r times the sine of theta, so I can just plug that right in. So this becomes r squared plus r times the sine of theta squared equals 6. R squared times 1 plus sine squared of theta is 6. And I guess usually we write polar equations as r equals something, so I can go ahead and play some rearranging games on this. And I'll get that r is the square root of 6 over 1 plus sine squared theta. I guess it should be a plus or minus there. But generally speaking, polar equations tend to take care of that without too much issue. So I'm not too worried about the specifics there. Just the idea of playing around and being able to take equations that are in polar form and rewrite them in rectangular form, take equations that are in rectangular form and rewrite them in polar form. Right, so with that idea in mind, I would like you to look at a very similar problem. I'm just going to switch up the addition for subtraction. So we have x squared minus 2y squared equals 6. And I would like you to play around with and write this in polar form. If you would like to, I encourage you to graph the original function in rectangular form and graph your solution in polar form. If the graphs are identical, that's a really nice way of double checking that you haven't made mistakes. But I'm not asking for the graph, I'm just asking for you to go through and do the algebra there. All right, so once again, I'd like you to take a couple of minutes. I would like to take myself back on screen. There I go. I'd like you to take a couple of minutes, work through that problem, see what you come up with, and I'll see you in the next video.